Hello and welcome to a new video. This is for middle school math using the Math UC Zeta curriculum, and we are going to do lesson 19 today, which is about solving for unknowns. But I feel like just jumping into the lesson itself is not necessarily how we want to do it. So I want to actually have us look at some questions that are you can think of them like brain teasers or things like that. So for instance, let's think about what plus 5 equals 8. So I would imagine this is probably something that you've seen before. It's supposed to get us thinking about like an addition, but in a different way, I guess. So what plus 5 equals 8? Well, you probably have there's a couple different ways you can think about it, but our answer here is 3. Okay, so either you realize that the connection here is that this plus means you actually need to do the opposite and minus to get your answer. So 8 minus 5. Maybe that's your thought process, or maybe you actually have problems actually even saying how you figured out. You just kind of knew. And so whichever way you worked it out, hopefully you got the right answer, because this is kind of a concept that hopefully at this point we're familiar with. A little bit trickier is when we do subtraction, and that's mostly just because of where we might put our unknown. So maybe we would say, what minus 10 equals 12? And you may look at that and you might say, oh, that's 2. But wait a second. If that's what your first thought was, because 2 minus 10 does not equal 12. Okay? Or maybe, like, what's another wrong answer that we might have gotten? I think that's the main wrong answer that I can think of. Because what we actually need to do, because we're subtracting, is we need to say, oh, let me add these together. We need to do 10 plus 12, which gives us 22. And then we can check 22 minus 10. Is that equal to 12? Yes, it is. So that's our answer, is 22. Now, what we do, I left a blank or I put a question mark. What we do as we get older in math is we put a variable there. A variable is just kind of a fancy name we use for a letter that represents something we don't know. X is actually the most common variable we use. And in fact, if you can see my shirt, I have Y's and X's on it, which is kind of the two most common variables we end up using. But any letter actually will work. So the problem with using X is that if we're using an X for multiplication still, it can get confusing. So as we introduce this idea of having a variable like X, we also switch to other ways of writing multiplication. So I could ask you, what is 3 times X, or if 3 times X equals 15, what does X equal? And just by the way, when we do this, we're doing algebra, which is really cool. This is what algebra is about. So 3 times what gives you 15? Now, maybe you are basically doing trial and error, thinking, okay, 3 times this, 3 times this, 3 times this. Maybe it's easier because 15, has to be divisible by 5 since it ends in 5. So maybe you're like, oh, it's 5 because 3 times 5 is 15. Or maybe you're going through the thought process that we'll build on as we get closer and closer to algebra of 3 times X means that I need to do the opposite and divide. And no matter how you ended up doing it, it is true that the answer is 5 and that we can get 5 by doing 15 divided by 3. Okay? So we have this idea of unknowns that we're trying to figure out what they are. We have this idea of the opposite operation. It will help us to figure out what it is. And so let's look at what our lesson is actually about. So our lesson in the Math UC workbook this week, which is lesson 19, actually basically has one kind of particular equation that we're using, and it also relates back to last week where we were dividing decimals. So this first example says 0.5x equals 12. Well, first off, if there's not anything between 0.5 and this x, then it's talking about multiplication. And again, this x is not an x like a multiplication symbol. It's an x as in this is an unknown thing that we just don't know what it is. Now there's actually, because it's 0.5, you might be able to come up with this answer without having to divide, because we can actually think, well, how many halves are there in a number that then would give us 12. Like what number, if we fill it in with halves, gives us 12? I don't know. That's kind of a weird thing. But the other way to do it is to divide, to say, I'm going to take the 12, I'm going to take that 12 and I'm going to divide it by 0.5. And we learned how to do this last week, right? We learned that it matters that the thing we're dividing by has a decimal. We don't want it to have a decimal. So we move the decimal place before we actually divide. So we take this and we say, how many places do I need to move 0.5 so that it's not a decimal anymore, so that it's 5 instead? I'd have to move it over 1 place, which means that we need to move it over 1 place on the 12. Otherwise, we've basically changed our numbers. But as long as we do it to both of these, then when we divide, we'll still get something that's true. So for 12, we need to kind of add another 0, or add a 0, because we're moving the decimal over a place. So what we're really doing is 120 divided by 5, which we may not be happy about doing, but we can do. Long division, for its terrible name, is still something that I think most of us are pretty capable of. And really, for me, it's once we do 2 digits or more that we're dividing by that is really where long division gets frustrating. So 5 doesn't go into 1, but 5 does go into 12 twice. And so we put it up above right here. We subtract 10 and bring down our 0. 5 goes into 24 times. So what I said earlier, that we could think how many halves or what number can we fill up with halves to get 12? I feel like there's a better way to word that I'm just not thinking of right now. So we could have come up with that actually by doing 12 times 2, to say that each of those 12s actually would happen, it would happen twice. And so we do 0.5 times 24, and that would give us 12. Let's do B. So 0.02y equals 51. So we're going to do 51 divided by 0.02. And it maybe it's easier if you don't put the extra 0, right? That it's just something we do sometimes. We put the 0 on the left side to kind of make it so the decimal is surrounded and make it, I don't know why we do it. We need to change this from 0.02 to 2. Our goal is going to always be to take the number we're dividing by and make it not be a decimal anymore. We want it to be a whole number. So in order to do that, we move this 2 places over. And what we're actually doing when we do that is we're timesing it by 100, just by the way. So if I do it to the 0.02, I also have to do it to the 51. So I move it over 2 spots. I get 5100. Now let's do 2 into 5100. So let's see, 2 goes into 5 2 times. And 2 times 2 is 4. So I subtract and get 1. Let's bring down this one. 2 goes into 11 5 times. And bring down the next 0. 2 goes into 10 5 times, but now we subtract by 10 and get 0. So this last 0, 2 doesn't go into 0, or it goes in 0 times. If you get to a place where you've subtracted and it's come out evenly and all the rest of your numbers are 0, you just need to make sure to put those zeros up above. So you wouldn't want to accidentally say that the answer to this is 255, because it's not. It's actually 2,550. And that has to do with the fact that we had to move the decimal over 2 places and us keeping track of our place value. 2 more, one of which is a word problem. Let's look at C. 0.0007a equals 98. So we're going to do 98 divided by 0.007. And that's because that's the opposite of what's happening here. It's saying that 0.007 times a equals 98. Well, that means whatever 98 divided by 0.007 is, that's going to give me a. So I'm going to think about, okay, 98 divided by 0.007. First off, how many times do I move the decimal place? I need to move it 1, 2, 3. 1, 2, 3. So that gives us 98,000. So we're going to do 7 into 98,000. And so say 7 into 9 goes once. 7 into 28 goes 4 times. And then all the rest of these are going to be zeros because 7 goes into 0 0 times, and we keep dropping zeros. So we just need to fill in the rest of these as zeros. So the answer to this is 14,000. So just like last week, by the way, because we're dividing by something that is smaller than 1, we're going to end up with our answer being something that's actually bigger than the thing we started with. That comma looks funny. I wanted to fix it real quick. So just keep that in mind if you're like, wow, it's a really big number and we started off with something super, like much smaller, like 98. What we're essentially saying is how many 0.007s can you fit into 98? You can fit a lot. You can apparently fit 14,000. So that's kind of what we're working with here. D. When Leo was 4 years old, he was 0.6 of the height he is now. If Leo was 36 inches tall when he was 4, how tall is he now? This is a completely made up situation. Leo is the name of one of the students in my son's class, and I don't currently have a student named Leo, so it seemed like as good a name as any. He's 4 years old. When he was 4 years old, he was 0.6 of the height he is now. So he's 0.6 of how tall he is now. So we'd put in a variable, whatever variable you like, but that's going to equal 36, because what's happening is if we knew how tall he was now, we'd times it by 0.6 and that would give us 36. So because we're missing his current height, we're going to solve for it like what we've been doing. And actually, all of the word problems in this section should be where you could set it up with the decimal number times variable equals whatever other information they give you. And so then we end up dividing. They're all really similar. So try to kind of look at it and be like, okay, well what kind of things is it asking me? Word problems are tough, okay? Or they can be. Typically, people like word problems less than they like other types of math problems. So just keep that in mind. We're going to do 36 divided by 0.6. So I'm going to move the decimal one place, move it one place, and add a 0. 6 goes into 360. We do 6 here and subtract, and 6 goes in 0 to 0 times. So our answer here would be 60 inches tall. So, which is about 5 feet, in case you were wondering how tall that is. So this is the gist of this lesson. I hope that we'll be building some more problem solving and equation solving skills as we go, but keep in mind we're not quite to algebra yet, so we've still got lots of room to practice and grow before we get there and really need to know how to do it. So I'll see you in the next video. Thanks for watching. Please give me a thumbs up if you like the video. Don't forget to subscribe if you haven't already. Thanks. Bye.